Hi and welcome to another electrostatics lesson. I am looking at electric fields in this lesson. Now, what is an electric field? I think this will also be a fairly short lesson. An electric field is an area in space where a charge will experience a force. Okay, now we know that a charge will experience a force if there's another charge that attracts it or repels it. So an electric field is a vector, it's a vector quantity. A vector quantity, what that means, it has direct size and direction, and the direction, okay, so size, okay, and direction will be determined by what a positive charge will experience. Positive charge will experience. I'll explain in just a moment. I'm sure you will understand. Okay, the size I'm struggling with spelling experience here. Okay, with experience. Great. So the size is going to be determined by the definition. The definition is going to be the force per unit of charge. Okay, so basically what we're going to do is we're going to use a unit charge. In other words, a unit means 1. Okay, and obviously when we talk about 1, we talk about an electron. Now the charge of an electron is given by Q. Okay, now even though we're looking at a unit as an electron, we are going to look at a positive charge. So we're not going to look at Q as Q is equal to 1,602 times 10 to the power of negative 19. Okay, if we talk about an electron, we will use negative. And even though we're talking about a unit charge, we're going to consider what will happen to a positive charge. So we're not going to look at an electron per se, but one positive charge will be a Q, but a positive Q. Okay, so we're going to look at one positive Q, and this is going to be one charge. So if we talk about the electric field as the force experienced per unit of charge, then an electric field is calculated as the force per unit of charge. Now, the one concept for me, that electric field is a whole region in space. But if I talk about an electric field in this sense, here I've got a charge. Let's do this. Here I've got a charge Q. Okay, a charge Q. Now, if I bring a unit charge, in other words, a small q, which means that this q has got this charge in here, he will either experience an attractive force or a repulsive force because this q is attracting or repelling it. Now, anywhere in space where this q is having experiencing a force would be called the electric field. And so we can see there's a whole region of space around this charge where this object will experience a force that's attracting it or repelling it. And obviously the closer I get to the charge, the stronger that force will be. Why? Because in the previous video we saw that this force that we're talking about here is equal to, so in other words, the force that charge experience would be equal to K, which was the constant. This is Coulomb's law, times the charge of Q times the charge of this object, which is just a single charge, so it's small q, divided by the radius squared. So the closer I get to my charge here, okay, the smaller the radius will be. Now if I decrease the denominator of a fraction, I increase the value of the expression. So the closer q gets here, the stronger that force will be. Okay, that's fairly simple and straightforward. And then the further I go away, the bigger I'm making my denominator, so the more the force will be. Another thing is, the stronger the charge is on q, the stronger this force will be. So again, we see that this electric field, okay, is a region of space around a charge that causes a unit charge, in other words one positive charge, to experience a force. Now that's a whole region of space, but again, at every point in this region the electric field will have a different value, okay, depending on, actually in little concentric circles, because it all depends on how far it is away from the center. Okay, so electric field is that whole region of space, but at each point I can go and calculate the size of the electric field, so it's not a constant just because it is experiencing a force. Okay, so I think that answers it fairly easily. And if I now substitute, I can either use this formula right here, or I can say, okay, well, F is given by K R squared divided by Q, and so the size of the electric field is given by and just so you can see here, the unit that I'm working with is newtons for force divided by coulomb for charge. So the unit is Newton per coulomb, like that. That's the unit for the electric field. The unit for force is obviously just Newton. Okay, and this one, if I now go and simplify it, notice that the q's can cancel, and I'm just simply left with K R squared. In other words, the size of the electric field, depending on how far I am from the center, only depends on the size of Q. Okay, that's the charge size in coulombs, and then the distance between the from where I'm measuring it. How far am I measuring it from away from the charge, and that is going to give me the force per charge that will be experienced at that point.